Okay, assalamualaikum and good morning, everybody. So today, this week's lecture, we're going to learn about how to create transfer functions. Okay. In this course, we will have transfer function in terms of electrical circuitry and also mechanical systems. Okay, if we check the Norman Nice book, actually they start with electrical, but here we will today start with mechanical system first, and in the next week we will learn the electrical system. Okay, so about this, the first thing to understand is that in mechanical systems there are three main types of components usually. Okay, one is the spring. Here in table 2.4 is the spring, and the force, you can check the table for the force velocity, force displacement, and the impedance equation. Okay, we will go into this more detail in the example, but for now just understand that there's three types of components for mechanical translation. One is spring, second is the viscous damper, and third is for mass. Okay, and it's important to understand from this table the force displacement. So you can see that if you remember Hooke's law, the force from this spring is F equals to kx. Okay, x being the displacement, and viscous damper, the equation is F equals to Fv dx dt. So the rate of change of displacement times with Fv. Fv is the friction of the viscous friction coefficient. It's a coefficient, like it's a number. And then lastly we have mass. So it's for mass, the equation is Ft equals to md squared xt over dt squared, which is effectively force equals to ma. Okay, because double displacement of this double derivation of displacement is acceleration, so F equals to ma, or d squared xt over dt squared. And then on the right side you'll see the impedance. So the impedance is the value for the Ft that has been applied with Laplace transform. Okay, so for the spring, the Ft is kxt, and then with Laplace transform it becomes k. Viscous damper becomes Fvs, and then mass becomes ms squared. Okay, later we will show you how you can use this to create the transfer function for the system, for the mechanical system. Okay, I encourage you to read more on this section by yourself in the book to get better understanding. Okay, so basically the important thing here is in the last paragraph you can see that we can now do the first example, which I will go through with you in a bit, and that the mechanical system requires just one differential equation called the equation of motion to describe it. Okay, so that's what we're going to do. Okay, so here is the example 2.16 from the book, where you are asked to find the transfer function xs over fs. I'll show you what that means later, for the system of figure 2.15a. So this one on the left here, you can see the mechanical system consists of a mass m, a spring k, and viscous dampener, which is Fv, and then there is a force applied to the mass that pulls it to the right, and you can see the xt up there showing the direction of the displacement, which is xt. Okay, so we're going to go through this. So the first step is we need to draw the free body diagram. The free body diagram will show or visualize all of the forces felt by the mass. Okay, and we assume that the mass is traveling to the right. Okay, so we're going to show it right now. Okay, just give me a sec. Okay, all right, so this is the mechanical system that's given to us. We have the mass, we have the spring, and we have the viscous dampener, and we have this wall here. Okay, and we have the this is the mass. Okay, so now we put it in a free body diagram to look like this. So here is the mass. Okay, and then we have the main force, which is the pulling force of Ft, and then we have three forces as a result of Ft. One is the pulling effect from the spring, which is K, hold on, which is K X T, and then we also have the effect of the mass inertia, which is m d squared x dt squared, and lastly we have, let me just fix this, yeah, should be bigger. We have the effect of the viscous dampener, giving you Fv dx dt. Okay, so you can see that there's one force going to the right, and all of the forces are opposing that movement. Okay, so we can say that the equation of motion will be looking like this: Ft equals to plus Fv dt plus K xt. Okay, so this is the equation of motion. Then we apply Laplace transform. If you remember Laplace transform, to get this in the frequency domain, and it becomes m s squared xs plus fv s xs plus k xs. Okay, so this is the equation of motion in frequency domain, and we were asked to find just now the transfer function, right? The transfer function given just now is xs over fs. So we need to factorize this xs out first, which gives us fs equals to ms squared plus fvs plus k. Now we have here xs. So to get xs over fs, you bring down the ones in the bracket, and then you bring f the other side, so you'll get gs is equals to 1 over m s squared plus fvs plus k. Okay, so this is the transfer function, as shown also in the example here. Okay, here you can see on the 2.16b, it shows the transfer function for this mechanical system, and I've shown you how to derive it, how to get it, how to get that value. So that's the first example. We'll go through the next one after this.